welcome to Uplink 38, Mark. What a pleasure to see you. It's been a big month, you could say. A lot of things happening now to bring it down to earth. You know what they say about buses? Yeah, you're always waiting for one, and then suddenly three come at once. So for anyone that isn't connected to the internet this week, what has been happening in the world of Mars?
Well, to understand what's happening now, we actually need to go back to last summer when 3 missions were launched towards Mars pretty much at the same time, and they're all arriving at pretty much the same time. And the reason for that is the alignment between Earth and Mars in their orbits. And these windows for sending missions to Mars the most efficient, effective way come around every 2 years. Mars goes around the Sun in roughly 2 Earth years, and when we line up in just the right way every 2 years with Mars. So 3 missions were sent last summer, and 3 missions are arriving. So in order of arrival, that's the United Arab Emirates HOPE mission, which is the first Arab satellite to go to Mars. It was launched on a Japanese rocket and is arrived and is in orbit, and that's where it will stay. It's an orbital mission studying effectively the weather of Mars. And then last week was China's Tianwen-1 mission, which is a very complicated full set of an orbiter, a lander, and a rover. Now, the orbiter's gone into orbit, it's arrived, but they're not going to put the lander down until May or so. So this is pretty much how it was done with the Viking missions back in the 70s. Go into orbit first, do some surveying, then go down for the landing. But what's happening this week is the 3rd mission that was launched, and that's NASA's Perseverance rover, which is, in some broad ways, but we'll get into this, a copy of the Curiosity rover that arrived in 2012. And that's arriving at Mars tomorrow. And when it arrives, it's going to go straight down to the ground. There is no orbiter. It's just the lander and the rover. In fact, not even a lander. It's just going to be this so-called sky crane. And we'll talk about this in detail. The sky crane, which then drops the rover onto the surface, and the rover just starts driving off. And that's happening tomorrow, which is why we're pre-recording and getting the show out a day in advance, because tomorrow everybody should be watching the actual landing occurring.
Indeed, fascinating events, and no 2 better guests to have along for the ride to explain what's going on. So who do we have joining today for people not familiar perhaps with ExoMars or planetary geochemistry?
Yeah, well, talking about the Perseverance mission, one of the things that that NASA is doing on this particular mission, which is different to last time, is it's got some additional instruments looking for potential signs of life on the surface. Now, that wouldn't be necessarily life in the present, but life deep in the past. And the first guest today is Sandra Siljeström from Sweden, who is a planetary geochemist, and she'll be working with the Perseverance team as one of 5 scientists from Europe who appointed by ESA and NASA to work on the Perseverance rover. The other guest today is Jorge Vago, who is the ExoMars project scientist. So ExoMars is Europe's joint program with Roscosmos, the Russian space agency. We sent a mission in 2016, which is in orbit today, the Trace Gas Orbiter. And the ExoMars rover was also due to go last summer, but due to some technical issues and also coronavirus, that got delayed until the next window. So that'll be launched in 2022. And that's got a much more capable suite of instruments for looking for life. But they come together, and the reason these 2 guests work together very well today is that Perseverance is also going to be caching samples, bits of Mars, to put on the surface, and then together, ESA and NASA will go and pick those samples up before the end of this decade and bring them back to Earth for analysis. So there's an awful lot of, it's not just one mission, it's a whole suite of missions going, and a program for finding out, is there life on Mars? Or was there in the past? Or maybe is there today?
Indeed, a big question, and arguably a fantastic song as well. So we'll be joined by Sandra and Jorge right now. Hello, Jorge. How you doing?
Hi.
Morning, Jorge.
Welcome. And Sandra, how are you doing? Are you receiving?
Yes, I am receiving.
Fantastic. From the deserts of Tatooine, it looks like. It's brilliant. Well, look, we have so much to talk about, but I guess we should probably talk with an obvious question. I guess, aside from where Mars occupies the popular imagination, and Mark, of course, has a fantastic background there from arguably the best adaptation of the War of the Worlds. From a scientific perspective, Sandra, why is Mars so interesting?
Well, I mean, it's one of the closest planets to Earth, and so it's quite easy to go there. And the second is that Mars share many of the characteristics of early Earth, or it's believed that the climate and that Mars maybe 4 billion years ago was much more like Earth, or actually Earth 4 billion years ago. So there is this. It's maybe one of the best possibilities in our solar system to find life, and we're talking here about microbial life. So.
Indeed. Well, it's an absolutely fascinating concept, which I think we all agree, regardless of what we find, it could completely change the way that we look at things, not just what's there, but also how we see ourselves as well. I think like so much of what all space exploration does. So, Jorge, it's an incredibly interesting week, an interesting few weeks, and so on. I suppose this has been a very busy one for you, keeping an eye on all these developments.
You're yes, very busy.
So Jorge, tell us, because at the moment, as I said in the introduction, ExoMars, of course, is not flying, is not arriving this time. That'll be in 2 years' time. But as a Mars watcher for many years, with 3 missions arriving at once and all doing different things as well, give us your perspective as somebody that's been thinking about Mars and working with Martian scientists, whatever that means, scientists who work on Mars. They don't come from Mars. What's your perspective at the moment on the arrival of these 3 missions all at once? I introduced all 3 of them, so Hope, Tian 1 and Perseverance before you came on, but give us your perspective. What are we going to learn in the broadest sense before we dig into the details?
Well, I regard this as a voyage of discovery and requires many steps, and each one of the missions, the past ones and the new ones, contribute knowledge that is very important. And here is not just learning about Mars, but it's also learning about the terrestrial planets and how they evolved. And Mars is a very good planet to learn from. So I would say that these 3 missions each have their own goals, but we have a lot riding on Perseverance, because Perseverance will be the first step of what will be the first attempt to bring samples back from Mars to Earth for study.
So before we dig in on Perseverance and Mars Sample Return, let's give some attention to UAE's Hope mission and to China's Tian 1. I think with Hope, we have a pretty good idea what it's doing. We have a pretty good idea of the instrumentation and, that it's effectively a weather satellite from large distances. Tian 1 we know an awful lot less about, right? And it's not to say it's a complete mystery, but, so talk us through Hope first and how that fits into things like Mars Express and the Trace Gas Orbiter, orbital missions, and then give us a bit of an insight into Tian 1. What do we know? And maybe Sandra, maybe you know more than I don't know that much about what's on board that rover.
Oh, you mean the Chinese one?
Yeah, exactly.
No, I don't know that much actually either. It's but there is instruments, and I know that one of the goals is to look for like signs of past life, and it does have quite similar, if I understood, like science objectives like Perseverance, looking for signs of life and characterizing geological the environment and habitability of that particular place. One thing we should think about is, why is there so many missions going to Mars? But still, we're only covering a very small part of it's like it's like you would send one, mission to Earth and land on, I don't know, like one particular place in the US, and you would say something about the whole planet. So we need several different missions going to several different places. Otherwise, you can't say anything about. You can say something about that place, but to get a more global perspective of Mars, you need to send several different rovers. So I think each of those rovers will complement each other, and because they will go just by going to different places, but also by having different instrumentation. But I think some of the instrumentation, I don't know how much details there are exactly on the instrumentation. Do you know more, Jorge, on the?
Well, I was asked to review a paper on the Chinese mission payload, so I've had a peek at the instruments they have and what they can do. And some of them are pretty impressive. In particular, the cameras, they have very, very high resolution. So hopefully we get to see some very nice pictures.
So that's on the surface rover. There's an orbiter as well. I don't think, again, I don't really know how much sort of gas chemistry, for example, looking for methane and these sorts of things that Trace Gas Orbiter is doing, our mission. Do we know? But again, I'm sort of desperate because, of course, we all want to talk about Perseverance, but I really want to make sure that Hope and Tianwen-1 don't get left out of the mix. So let's just go back to Hope. What can you tell us a little bit about the Hope mission, Jorge?
Well, to me, the most interesting aspect of Hope is that it will observe Mars from a place, so relatively far away from the planet, that allows us to have a more or less a global view of the planet. And this is interesting because it will provide information that we don't get with the other missions. Normally, the ones that would like to go for very high resolution analysis of surface features, they have to be very close to the planet. Typical altitude is in the order of 400 kilometers. Here we're talking tens of thousands of kilometers away, and it's interesting for trying to understand, for example, what is the onset of global dust storms, for example, and things that when you have your nose so close to the surface, you cannot study that well.
So let's just place that in context for a moment. You mentioned the global dust storms, and we saw one in the last summertime, I think, on Mars, where there were huge dust storms covering the planet. And the science fiction link is to The Martian and Mark Watney getting trapped on the surface and their spacecraft being knocked over by a dust storm. So, which is nonsense, but give us a bit of feeling. Why is that the case? Why is a dust storm like that not a dangerous thing on Mars in the same way as it might be on Earth?
Well, Mars' atmosphere is very thin. So here, for example, we have a surface pressure of a bit over 1,000 millibars. And on Mars, the typical surface pressure is just 6 millibars. And to put that in perspective, if you have a wind of 100 kilometers an hour on Mars, it will push like a wind of 1 kilometer an hour. So yes, you can have dust storms and you can have high-speed winds, but there is no heft to that pushing, and so the antenna wouldn't have flown off the top of the base and skewered Matt Damon as it does on the movie.
Ah, what a pity.
For so many, perhaps the first time they've really thought about Mars in that way. Beyond, obviously just like the sort of you could say even less accurate kind of science fiction out there, and so interesting and thought-provoking. And I guess to bring it back just to like the wider view beyond the science, why so much now? Or has this just appeared to be a sudden burst of activity? Why so many missions currently? Because it does seem that it is a focus of planetary exploration, whereas other planets are not.
So, Sandra, you have to defend Mars now, because I'll go full Venus on you otherwise.
Okay.
Well, I mean, it's the practical that, I mean, that we have three, in the same month. It's just the practical, that every second year it's the closest approach between Earth and Mars. So it's kind of convenient to send off those three missions, and this kind of tends to, accumulate the different missions, right? So the last cycle there was at least one InSight also. The NASA InSight lander. But I think there's more focus on space in general, right, with all the launches and stuff. There's also an increased intention in going back to the moon, and I would say, like, after you've gone to the moon, Mars is kind of the next logical step, right? If you want to test your capabilities and you want to, and of course, then there's this obvious, the possibility of life on Mars, which is obviously very interesting to explore. So I'm sure Jorge has additional maybe views on these questions, right? So
there is also the fact that these space missions are regarded as way for countries to show that their technological capabilities, and we are at a time when many countries are able to undertake this sort of challenging mission, because landing on another body is complicated. And so it's a statement, we can do it. And I think that
and I guess, like, after landing on the moon, the next step is to land on Mars, because it's quite easy to land on the moon compared to Mars, because you have this atmosphere you have to take into consideration when you're landing on Mars versus the moon, right? So
yeah. Plus a deeper gravitational well. Mars is a bigger body, and so gravity is higher there than on the moon. That also makes it more challenging.
So let me pose a question, though. I mean, is there also a fascination with Mars? As Sandra said, it shared much more of characteristics with the Earth 4 billion years ago, potentially, than it does today. But even today, I mean, that picture in the background that Sandra has is Namibia, not Mars. But you could see a picture of the surface and see something very similar on Mars. We've seen sunsets on Mars. It looks temptingly similar to the planet we live on. And even before we had those beautiful images from the surface or from orbit, there was this fascination going all the way back to the canal on Mars or not. This idea that there might be life on Mars and it might come and invade us, so hence War of the Worlds. Do you think that, in the space agencies, we also, to some extent, use the human fascination with Mars, which is independent of the science, but is something about and Mars, of course, has a history which goes back thousands of years as the god of war, for example, this thing in the sky that's red. I mean, how does it feel? Did you ever place yourself outside being a scientist and ask that question from the human side? Say, are we fascinated in it because somehow it's connected to us in some philosophical way?
I guess one fascination is that you can see it quite clearly, and that it is that red spot compared to the other most of the other objects, except Venus, which is of course very obvious, but still because it's red, it's kind of fascinating. It has another color, right, compared to the stars and such. So I guess it's always kind of made itself obvious on the sky, even to the ancient Greeks, that this is something different because it has a different color, stuff like that. So and it's also kind of on the way out. I don't know, maybe it's more interesting to go out of the solar system than in towards the sun. I don't know.
I think that we sort of project ourselves, and part of the fascination of Mars is that you feel you could walk there, you could go there.
You mean compared to Venus, which would be
exactly, which is it's a hellish place today for to think of sending an astronaut. I also
Maybe
think,
it's also because you can't really see the surface on Venus, because of the clouds. You just see all the swirling clouds, right? So
well, you could if you were on the surface, because the clouds at a certain altitude, they're not there, and then you can see. But now, the other thing I find very interesting about Mars is that I joke with some of my colleagues. I always say that the moon is black and white, but Mars is technicolor. There's a lot to see that we can connect to. All these ideas of possible ancient seas and river systems. There are many things that we recognize from our own planet. At the same time, is alien enough to make it fascinating.
I mean, I agree. It's like, with the landing site of the Perseverance rover, where you can actually see that it's a delta. You have this crater, and it's been obviously filled with water, and it's a delta, like you would see on Earth, for example, the Nile Delta or something like that. And it's even for someone who's untrained, it's pretty obvious, so.
I wanted to, before we sort of go in on Perseverance and then ExoMars, I wanted to come back to some of the technicalities, because you talked, Sandra, about the landing site for Tianwen-1, and this is in Utopia Planitia, which is in the northern hemisphere. It's the same place, the same broad region where Viking 2 landed back in 1976. And I wanted, Jorge, give us a feeling, because that leads us into Perseverance. Why has China decided to go to Utopia Planitia? I mean, it's, leading questions. It's to do with it being big and empty and flat, and also at low elevation, right? And these are important things when it comes to your first landing on Mars, which is different to what Perseverance is trying to do.
Yeah, I think so. Initially they considered also another area, and we helped a little bit with Mars Express, providing some data to help them with their mapping. I think Utopia Planitia is an interesting target to go to. It's a very old region of Mars as well. There are, at a certain point, we were considering it for ExoMars as well. It was one of our candidate sites. So certainly landing low is important to have sufficient purchase in the atmosphere for your parachutes.
Give us, this is one of these points where I jump in and explain what that means on Mars. You've talked about the 1% atmosphere, but the one thing we tend to forget about Mars is that it has very high peaks, Olympus Mons, and where on the Earth we'd have the bottom of the oceans, you have land on Mars. And that what's the distance, the difference in altitude between the highest points and the lowest points on Mars?
Oh, well,
broadly,
they're in
right?
different places, but Olympus Mons is some, if I remember well, some 25 kilometers high. And the deepest point in Hellas Basin is minus 13 kilometers. So that's a lot of altitude range.
Yeah.
But the other thing to remember is that the pressure, the atmospheric pressure at the surface of the planet on Mars is the equivalent of what we would have on Earth at 30,000 meters. So when it comes to slowing down, like with parachutes, for example, you don't get a lot of braking power from such a thin atmosphere. So you need a lot of it to actually reduce your speed.
So that takes us on to this issue then about, how do you land on Mars? It's not the same, for example, as landing on Venus, where the Venera probes dropped under a parachute and then basically just let go, and they just drop through the thick atmosphere kilometers just with nothing, just through the thick atmosphere. On Mars, it's totally different, right? So there's the three classical stages. Talk us through the three classical parts of how you land on Mars.
Yeah, it's. I always joke that I say that on Venus and Titan you can land with a handkerchief. because the atmosphere is so dense that it's like landing in a swimming pool or something like that. No, on Mars is very tough. So typically, the way we do it these days is we arrive from the hyperbolic trajectory and we slam into the atmosphere at some 20,000 kilometers an hour, which is not what Tian 11 is doing, by the way. They are going first into orbit and releasing from orbit. So there, the arrival speed is a bit low. But for missions like Perseverance or ExoMars, you arrive at roughly 20,000 kilometers an hour. And the first half is what is called the hypersonic stage. And basically you use the heat shield at the front of the capsule, and by friction with the atmosphere, you slow down from 20,000 kilometers to roughly 2,000 kilometers an hour. At which point you start deploying your parachute, which typically, Perseverance has one, ExoMars has two, but the first parachute is always supersonic. And that will slow you down to a speed of roughly 300 kilometers an hour, more or less. But yeah, that's still going pretty fast. And at that point, there's no other parachute or bigger parachute you can deploy. You have to use something else. And so the last bit of the landing is done with descent engines that slow you down to a final touchdown speed that typically is less than 10 kilometers an hour.
And just to sort of dig in a bit deeper, so in the past, the Viking missions, for example, they had retro thrusters which descended right to the ground. And ExoMars, the rover in 2022, will use the same strategy, descend all the way to the ground on a platform, and then the rover drives off. Previous NASA rovers have used this airbag approach, where they come in and then sort of let the thing bounce across the surface crazily, it seems, for minutes, bouncing high up in the low gravity. But Perseverance uses this crazy sky crane scheme, and it's crazy, but it worked once already with Curiosity. Why? Just talk us through that before we get to the surface and start talking about the chemistry. Talk us through how that works and why they need to use that. Why airbags or other strategies are not the preferred one for for Perseverance.
Well, let me start by saying that NASA has perfected the landing site or the landing procedure over many missions. And what they do is very, very clever. So typically, if you land, the typical low-cost mission will land sort of like a rock. You just go ballistic, which means that the spread of your landing ellipse on the surface of Mars is relatively long in the direction that you arrive, say 100 kilometers by 10. So NASA uses this approach for their smaller missions like Phoenix or InSight. But for their super duper missions, they use what is called guided entry. And in guided entry, you have a special shape of capsule that allows you to make lift like a wing. And so they fly these S's like the space shuttle did, very high up in the atmosphere, and they lose most of the speed very high up, and then they drop like a rock. And then the resulting landing ellipse is no longer ellipse, it's more like a circle. So with Curiosity, they had a precision of roughly 20 kilometers, but with this mission, they're going to do much better. They are aiming for 7 to 10. And not only that, but they also have obstacle avoidance, which means that there is a camera looking down that has on board a map of what the surface of a landing site should look like, and is comparing constantly what it sees with what it thinks should be there. And if the spacecraft predicts that it's going to touch down in a place that is complicated, you can fire the engines or maneuver, let's say, to go somewhere else. It's very, very nice.
Yeah.
Yes.
Can I ask, just a question from the Martian perspective for a moment there? Because we talk so much about putting things down onto the surface of Mars. Let's say there is life. Let's say that there is something there. Is there an environmental impact that has been considered? Is there a potential issue there? Because if there is life, it means there is an ecosphere. How will we address that?
What do you mean, like an active?
Yeah, if there's anything there, how do we know that we're not going to actually damage what's down there?
Well, I mean, there are all these planetary protection requirements. So, for example, Perseverance has been cleaned to a certain, there's very defined, requirements for covering everything from, inorganic elements all the way to organics to, number of spores. And they cleaned this. I think it's been very cleaned. So this is one. This is and this is to also protect the sample that Perseverance will collect, because you don't want to collect whatever we brought to Mars. We want to collect whatever's on Mars. So we have to have it. Then we also have these witness plates and stuff like that to kind of track the contamination. But in terms of protecting we're only landing on one particular site. So if that would be the only place that this active life is, we're kind of also, first of all, we're not going to these special regions where there are active water. So these are the most likely, because these have much higher requirements of, actually you have to clean your spacecraft to an even higher level to go there. So these are not, first of all, avoided kind of to protect, these potential life. And in terms of, sure, we might land on, a bug, I guess, and then kill it. But, it seems kind of unlikely that we would, destroy just by landing there, and then, of course, there's so I guess we're doing as good as we can to, it's considered in this forward contamination that we don't come and bring something. But of course, it's always, we could bring something and that could potentially then, is that what you're asking, that we might bring something that would colonize?
Well, absolutely, because of course, there's probably no greater sci-fi trope in the 20th and now 21st century than invaders from Mars. But from
this is if we bring stuff back, right? So
Indeed.
this is backward contamination.
Indeed. So we're the invaders from Earth, but I mean that, of course, in a positive way. The implications of what we're.
But it goes both ways, that we protect Mars, and then if we bring something back from Mars, protect Earth, and this is all considered, So.
But this is this trade-off, right? In Jorge, of course, we have an active planetary protection office at ESA.
Yeah.
It is this
so
issue.
I should refer these questions to ESA.
No. It's fine, because we'll come to the chemistry part in a moment. It's that balance, right? You want to go to a place where you maximize your chance of finding life in the past or maybe in the present, but at the same time you don't want to go to places necessarily where everybody's sitting around an oasis, enjoying the sunshine and the water. Not that probably exists on Mars, but so there's that balance. And some missions are less clean. They go to places which we think there's less chance of being life, and that's not just Mars, right? It applies to the moons of Jupiter or the moons of Saturn. It applies to the moons of Mars, right? This whole question about, can we pollute Phobos, for example, or should we, if we go and get samples back from Phobos? So talk us through what the process is.
Contamination would be, it's also for all that goes to Mars and doesn't bring anything back.
Yeah.
Right?
No, absolutely.
So
and
this
in fact,
applies for
Yeah.
And it should be I kind of tried to make that clear, that Perseverance is actually not looking for extant life; it's looking for extinct life. So actually fossil life, because it's considered quite unlikely that it would have extant life. And the drill cores that Perseverance is taking up, they're not that deep. So if the most likely place to find extant life would be much deeper, I would say in that case ExoMars would have a more likely it would be more likely that ExoMars would find something because we're drilling up to 2 meters. Why this is, I mean, it's a couple of centimeters. So
yeah. So let's just quickly make that clear, because NASA's done a very good job, of course, of saying this is all about finding life on Mars, which has annoyed me a little bit because it's not quite what it's. Yes, maybe, but it's not really the same mission as ExoMars in that regard. But before we go to ExoMars,
both have like looking for extinct life, right? So.
They do. But the drill, as I would say. So anyway, but Jorge, let's talk briefly about how do we go through those layers of planetary protection? How do we inform the science to protect those places we're going to from because our life is very good and very tenacious. Our life has evolved to fill every ecological niche, and maybe on Mars it's much, I don't know, weaker is the wrong phrase, but much more tenuous perhaps. So how do we go through that process? What's the scientific consultation?
Well, there's basically two things we want to do. First of all, we want to avoid getting the wrong results, because our spacecraft were dirty and we ended up discovering something we brought with us. But we also want to protect science for future generations. And that is also one of the reasons why we wouldn't want to have our own microorganisms propagate on Mars. So basically there's three categories of cleanliness that spacecraft going to Mars that are not bringing samples back have to deal with. The lowest level, which is called 4A, is like what Spirit and Opportunity had, the MER rovers. And that is, you're going to a place where you don't think there is life, you don't think Earth life would be able to propagate there, and basically you're looking at the rocks and taking pictures. So you clean your spacecraft very well, you just go. The second type is what Perseverance and ExoMars are, is a mission that is not going to a place where you think there may be life today, a place where you don't think Earth microorganisms might propagate, but you are looking for signs of life. And therefore, it is super important that whatever results you get regarding the possibility of past life not be false. And then very, very special high cleanliness requirements apply to all the parts of a spacecraft that come into contact with the material you want to study. So for example, in the case of ExoMars, it would be the drill, the sample processing system, the instruments that deal with the analysis of the data. So Perseverance is everything that has to do with the end
sample
of the
collection.
Yeah, the sample.
So it's basically the same, like the drilling and stuff like that, but with the added of the sample tubes. It's also have very higher requirements. So.
And the highest requirement, that there's been only one mission that ever had to comply with that, and those were the Viking landers, is when you go to a place where you think there may be life. Of course, at that time, nobody knew much about Mars. So the assumption was that for the Viking landers was that they were going to find active microorganisms. So they prepared for that eventuality. And then in that case, you have to sterilize the entire spacecraft. And in the case of Viking, they got the landers and put them in a giant oven in Cape Kennedy and cooked them for 4 days to temperatures higher than 100 degrees. A spacecraft wouldn't be able to take that today. Also, the plastics and the detectors, they just don't like that sort of very high temperature.
Right. So, Sandra, let's come then to the differences between what Perseverance will do in its search for extant life, and then to ExoMars, which has its unique features as well. And I particularly just wanted to start, from your perspective as a geochemist, right? You've got Mars is full of weird chemistry. So Jorge mentioned Viking. Viking, there was a thought that it did find life, but we now know that it wasn't finding a signal from organics. It was finding it from other weird stuff on Mars that we hadn't anticipated. So talk us through what your process is. How does a geochemist look at Mars and say, how am I going to find signs of life 4 billion years ago? What are you going to look for?
Yeah, so you were mentioning extant life here, but I guess we're talking about extinct
life now.
Yeah. Just to make it clear. And how do I look for? Because it's a different process if you're looking for extant life or extinct life. So, certain things you're kind of looking similar, but I mean, in terms of like, I mean, you kind of look for the first the requirements for life. I mean, does this place does it indicate that it has, some kind of water activity, a long time ago? For example, in Jezero crater, you can see it's a crater, it's been filled with water, and a big advantage is that it has this delta that kind of accumulated stuff, The delta is very good because you have everything that was happening in the lake, right? And maybe there was some active microbial life living in the lake, but you also have everything that was brought in from the larger region accumulating. So I'm kind of an organic geochemist, so I look very much for organics. So as we know it, I mean, now the assumption is that this life is made of organic molecules, and that's kind of the building blocks of life as we know it. And so we're looking for, so that's one of the things we're looking for are, organic molecules, and not
and just to be explicit, organics in this case is complex chains of carbon, oxygen, and hydrogen, right?
Yeah, so basically I tend to call, carbon-based molecules, basically, but typically it includes nitrogen, oxygen, and hydrogen, and sulfur, and phosphorus. So, and you would also look for those kind of elements, right? And then you would kind of look for organics, and those, and you would, but not all organics or these carbon-based molecules are from life. You also have some what they call abiotic processes, so processes that produce this without any biology involved. And so you have to look for patterns of these molecules. So because life, we don't use the whole range that exists. So you can have, there are millions of different of these type of molecules. That's why life using it, because you can get such a diversity of these type of molecules. So we're actually looking for accumulations of certain molecules, because life doesn't use the whole range. It picks certain ones. And if you get we have this, for some reason, this type of molecule is, has a very high abundance compared to other molecules. And that would suggest. So that's one of the ways. I mean, you also look for other type of chemistry, do you have the, the elements you need, the carbon and the oxygen, and but also kind of elements that might be used as, for energy for life, because if you're looking for any life, you wouldn't expect it to maybe use the sun, but you would use some chemistry with one type of, substance and make another substance, basically oxidizing or something. So you might look for that, and you would also look for morphology, and preferably you would kind of look for the combination of this. You find some intriguing structure, you found that it has carbon and oxygen and all of those elements, and maybe enrichment of certain metals, because life tend to pick certain elements, for example, using iron and stuff like that. And then you also find some organic molecules that are, have a particular pattern. So that's kind of how you look at, and this is the same process actually using when you're looking for very ancient life on Earth. So one thing you should think about is when we're looking for life that might be, 4 billion years ago. Even looking for this life on Earth is very difficult because and we're not talking about dinosaur bones here. We're looking for, small cells, and these kind of round structures can also be made by other things that are not biology. So a lot of these are very controversial, or you kind of see these wrinkles from, for example, it's called these stromatolites. It's kind of these microbial layers of sediments and microbial layers that creates this nice structure you can see in old rocks. I mean, the one thing though that are actually advantages with Mars is that it actually has the rocks are actually more fresh. The old rocks are more fresh than our Earth, because on Earth we have, you know, continents going around. So we have all this plate tectonics, and this will, you know, cook rocks. So actually a lot of the signs are, especially organic molecules, for example, might be very, you know, it has changed from the original molecules. So it actually might be easier on Mars to find these preserved in older rocks. So this is, so it's called, these are kind of combined, called biosignatures. So these are different. So it ranges from morphology all the way to, you know, complex chemistry, basically, all the way to, you know, molecular, like you would, if you would say, if you were looking for X-band light, you might then also look for some, use some DNA and
Okay.
type of.
So let's jump to Jorge on that. You know, Perseverance is going to do it all. Why should we bother sending ExoMars in 2022? What's the point, right? It's gonna. That's a leading question, you know that, right? But what's the difference?
That one too.
what's the difference, right? You know, what's the big deal about ExoMars 2022, and why should we be excited about what the Rosalind Franklin rover is going to do?
Well, first of all, let's explain what the damaging effect of ionizing radiation is on Mars. So we have radiation. These are high energy particles that come from the center of the galaxy that bathe the solar system. And normally, if you have a thick atmosphere like we have on Earth, this ionizing radiation is stopped way up in space. But because Mars's atmosphere is so thin, it penetrates through the atmosphere and actually penetrates also into the soil. And the effect of these high energy particles, they're like bullets from a machine gun. So you have your nice biosignature lying there, and you're shooting at it with these high energy particles that basically cut off the various functional groups and degrade your molecule to such an extent that eventually you cannot tell what it is anymore. So if you can think of this effect acting over many, many millions of years, it's a challenge. So detecting chemical signs of life on Mars is a mess. And it's a mess for many reasons. The first of all is, Sandra explained that we have abiotic organics, or organics that come in the form of cometary dust and meteoritic dust. All the planets get in the order of 240 tons of organic matter delivered to the surface as a very fine rain of dusty particles. And this accumulates on the surface. And because it has nothing...
240 tons a day, right?
No, a year.
That's per year, 240 tons per year, okay. Sorry, go on.
Did I get that wrong? Yeah.
It's lots anyway. It's over millions of years. There's lots of stuff from outer space.
There's a lot of stuff.
So this stuff accumulates on the ground, and it's a background that you have to deal with. Whatever it is that you find, you know that you're going to have some of these abiotic organic molecules mixed in with everything else. That's one thing. The second thing you have to deal with is assuming there may have been life. Perhaps it was active 4 billion years ago. And so these molecules that were encased in rocks after the microbes died, they have to make a trip in time from 4 billion years ago to you. And during this time, they could have been bombarded by radiation, pressed by all the material that accumulated on top, that could have been 1,000 meters of rocks on top. Maybe it was exposed to the effects of water or other stuff. So how these molecules have been affected is also very, very important. So one of the key aspects of Rosalind Franklin is we looked at what would be the damaging effect of this ionizing radiation on things that are close to the surface. And we realized that it would be almost impossible to find very, very, very old biosignatures in the good state of preservation if they're very close to the surface, because the ionizing radiation would have damaged them. So the idea of ExoMars is that, yes, you can study the rocks, what we call outcrops, that you see on the surface to tell if that's the right sort of mineralogy you want to address. But then what you do is you use a deep drill to go and collect your sample deep. The reason is that you can use all the material on top of the sample as sort of a natural shield against the effects of radiation. So, of course, this is, for now, is a hypothesis based on the best that we can tell today, but we will be able to tell if that is the case for sure after we start analyzing the samples.
If I could just ask a very quick aside here, one of the things that's always very apparent about so much exciting research that's happening is that it is on the basis of so much work that's been done previously. I mean, talking about Viking gives us some sense of, just how long it's preoccupied, exploration. But we mentioned someone, Rosalind Franklin. I wondered if we might just for a moment acknowledge who she was and why was her work significant? What's her connection with Mars?
Should I answer this? Or?
Please.
Go on. Yes, why not?
Well, she was the one that who actually took the the X-ray image of the DNA molecule. So she was key for. She actually did the taking the picture of that DNA molecule, so that Watson and Crick got the Nobel Prize for discovering the structure of DNA. To actually figure out how the structure was, but she was the key for taking the pictures they needed for doing this. And I mean, she wasn't really she wasn't included in the Nobel Prize. It was only Watson and Crick. So that's kind of, and it's kind of ignored that her contribution, I would say, to the discovery. So I guess one of the reasons, and I guess naming. I guess Jorge might, because you're actually representing ESA, what the idea behind giving the rover this name. So I can understand, but I want to leave it to you.
Well, we tend to think of her because of the discovery of the structure of DNA and RNA, but she was also very active in the field of understanding carbon, and she started working on coal. And after she did the work on crystallography, she also went to work also a lot on microbes. I think she's a hero, and she's also a very charismatic female scientist. We were very, very happy when the name was selected.
Just so everybody knows, it was a public competition, right? So it was an engagement exercise run. People get to propose names and propose why, and Rosalind's name, came out on the top there. So that obviously, I completely agree. It's a perfectly appropriate name. Let's jump back to the issue then. So ExoMars will drill down 2 meters underground, pull samples up, analyze it on an onboard laboratory, very complicated, sort of a miniaturized version of a full lab that you would have on Earth. But okay, we've been as brilliant as we can be. Why then do we need to bring stuff back? So let's go, Perseverance is going to cache samples, leave them on the surface for a few years. And that, of course, has got its own questions. Is it a great thing to do to leave them on the surface in little metal tubes? But then we're going to pick them up, bring them back to Earth, and analyze them, in ways that we can't do in an in situ situation. But so talk us through Mars Sample Return, because of course this is not just NASA. This is where European Space Agency and NASA come together. Talk us through the architecture, Jorge, of how MSR is going to work, and you know what the long-term goals of that program are.
Well, the idea is, as you said, in the 2030s to get these samples back and be able to analyze them with everything we can throw at them in the very best laboratories we have on Earth. And indeed, it's a lot that we can do that we are not able to accomplish with robotic missions. But
can I interject there a little bit?
Yeah, sure.
Yeah, because I mean, you have all these constraints on. I mean, there are great instruments on the rovers, but I mean, you have all these constraints. I'm talking here as a lab scientist to actually analyze Martian meteorites on Earth. But it's still, miniaturized and maybe simplified instruments compared to what you have on Earth, so if you can make a comparison with like the lunar samples, you take them back and they still haven't opened all the tubes. That some of them are still sealed, and this is because they kind of think, well, we have the instrumentation now on Earth, but we'll have, even more advanced instrumentation in, 20, 40. We don't even know, right? We can't even imagine what kind of instrumentation. So you're bringing back samples, and you will be able to do research on these for, maybe hundreds of years. So this is one of the large advantages, and the lunar research has been, greatly advanced due to that you brought back the samples during the the Apollo missions and such. So
I mean, just to be clear, when we talk about instrumentation, we don't always talk about better is smaller, because there are certain facilities like X-ray synchrotron facilities which require
can't bring a synchrotron to Mars.
accelerators a kilometer across, right? You're just not going to do that, right? So Jorge, jump back to what's the architecture of Mars Sample Return? We know that when Perseverance lands tomorrow, hopefully successfully, it will start in the coming months, moving around, looking for samples and leaving them. But that's just step one. So what are the other steps in Mars Sample Return?
Well, the challenge is you need to land a large lander with its own rocket to shoot the samples back into orbit around Mars. So that's the first major launch that we're going to have with the Mars Sample Return proper, so to say. And that lander should include a European rover called the Sample Fetching Rover that should go and collect these samples that Perseverance will leave on the surface and bring them back to the lander to be sent up. Once they are launched, and the launcher is something provided by the US, a European orbiter will dock with a sample sphere, collect it, and bring it back to Earth, where land on a capsule. The capsule is provided by NASA. And so it's a complex mission in that it requires two major launches, one for the lander that will land on Mars and another one for the Sample Return orbiter. And there is also quite a mixture of elements on both of these missions that are provided or by NASA or by ESA.
So, just to be clear, Perseverance is sort of not going to clear up behind itself. It's going to drive across the surface, chucking things out and leaving them. Somebody has to go and grab them later on, and that's the Sample Fetch Rover. And then, as you said, there's kind of this Matryoshka approach. You fire a rocket from Earth, and inside that is a thing with a re-entry shield, gets to Mars, and inside that is a rocket which then fires up, and inside that is another re-entry shield. That's not quite true, right? Because the samples come up from the Martian surface and then are encapsulated in the thing that will then re-enter the Earth's atmosphere. Is that right? So it's all that complicated docking, and which we've sort of seen with Ryugu, with the JAXA Hayabusa 2 mission.
Right? More complicated. because on the other missions, the systems had lower gravity, the asteroids they were visiting, and so you could accomplish everything with one spacecraft. If you like, it's similar by a much larger scale. So of all the stuff that lands on the surface of Mars, in the end, the only thing that remains from that very first lander mission is just a sphere with the tubes orbiting around Mars. And then this other very, very large spacecraft, which is the Sample Return orbiter, comes and has to match its orbit with that of this sample ball, and match also velocities, and slowly approaches the ball and captures it. And then a part of that spacecraft is left on Mars, and another part shoots back and goes back to Earth. And that includes, first of all, the sample has to be welded inside another sphere, and that is done in space. Then it's transferred onto this return part of the spacecraft, which also includes the capsule, and that separates and comes back to Earth. So complicated.
Yeah, I suppose in some ways, what's interesting, we talked about Tianwen-1 at the beginning. Tianwen-1 isn't bringing back samples, but China has already practiced some of these maneuvers for sample return as well by doing it with Chang'e 5, orbital maneuvers. And of course, the problem is at Mars, it's so far away from Earth. This is all autonomous. All of this docking has to happen on its own without anybody steering or driving things around. But I want to come to the point which we've already addressed a couple of times. When we bring those samples back to Earth, and that's forward contamination, the possibility that there's something in those samples which might be bad for us, we have to take that very seriously, right? We have to protect our planet. But rather than talk about that, I want to talk about this sort of bigger question. We've talked about life in the past. What are the chances that there's life on Mars today? It's the name of this week's episode of Uplink. What do we actually think that there, microbial life? Nobody's talking about aliens that can invade us, but what are the chances that there's life on Mars today, and what form would it take? What would the signs be? So Sandra, let's start with you. Imagine, you've got, what do you think the chances are that it's still there today?
Maybe I can answer the question of what form it is. It's microbial life. It's going to be like, a couple of cells. Maybe they form some colonies or something. And I don't know. I would say it's very, very low, the chances. And my approach is to be very skeptical. It's, if we're going to say that, so we bring back the samples and there's actually some extant life in those, or whatever, there's something on Mars. You have to have extraordinary evidence to make this extraordinary claim. And someone saying, "Oh, I'm seeing something and I think it's life," it's going to be like, checked and rechecked and triple. It's not. It's going to be a whole team, looking at that, and you're going to have several different evidence, because one of the things is going to be, are you sure you're not seeing terrestrial life? That we brought there actually. So it's going to be a very long process, and I think it's I don't know, maybe, I think the most likely is actually in the subsurface, maybe in some cave or something, and we're not really going there, so we're probably not bringing that back. So I don't know, I tend to be quite skeptical, just to like, then someone has to to have that approach that the most likely there's no life, and now prove to me that there is life. Do you see that? Like,
yeah,
because
sure.
Otherwise, if you're kind of like, I think there's life, so I'm going to prove, it's going to kind of lead you in the wrong direction, I think. So.
Yeah. But Jorge, we have this whole business of methane, which is still unresolved, possible biogenic, generation. My thinking on this is that,
even though there are a lot of different possible abiotic sources for that, and there are a number of different, there's probably like 10 different theories of how you can produce it non-biologically.
Sure.
So,
and we've seen that with phosphine on Venus as well recently, right?
Actually, I think there is a reasonable chance that there may be life on Mars too.
Extant life.
if you drill for oil on Earth, and you go 2 kilometers down, you find life even even more than 2 kilometers. These are, microorganisms that feed on certain minerals. They never see the light of day.
But you should
All they
remember
need is
that an oil source is a lot of
water.
stuff to eat for a microbe. So
Yeah, but these guys, the ones I'm talking about, these chemotrophic things, they not necessarily eat organics. They can metabolize iron or sulfur, very simple organisms. If life appeared on Mars 4 billion years ago, more or less at the same time as it did on Earth, and when Mars started going south, so to say, when things started to get dry and the magnetic field went away and there was no longer any water, it is conceivable that as if there were aquifers in the subsurface, that some microorganisms could have found refuge there. So it's going to take a long time before anybody drills a hole more than 1,000 meters deep on Mars, but I wouldn't discount it necessarily. Maybe 300 years
I'm not
from
completely
now,
discounting it. I'm just keeping a skeptical.
Yeah.
Yeah, I mean, I like this idea, of course, that if it ever started, the one thing we know on Earth is that life is adaptable. I mean, it's this question about extreme environments, right? Saying that because life in an extreme environment it can survive on Earth, well, that's evolution that's allowed it to evolve to work there. It doesn't mean to say it was born there, not at all. So when we look at exoplanets and say, oh, but look, it's just the same conditions as we find life in Antarctica, it's like, well, yeah, but life didn't form in Antarctica, probably. Whereas Mars, if there's extinct life, maybe it's found a way to cling on and survive even as the conditions have changed. And I think that's sort of the thrilling thing.
Yeah.
But I wanted to throw a sci-fi idea out, at least from my last question before Alex wraps up. Because, of course, one thing we haven't ever talked about is the Mars meteorite, ALH 84001, which was 25 years ago now thought to contain signs of microbes, tiny little structures, and Bill Clinton made a big deal out of it. And it all turns out not to be the case, but okay, that's science, you learn. But that idea of things traveling between Earth and Mars, the fact that there are bits of Mars on Earth today, we don't need to go to Mars to get samples. Okay, we do for lots of other reasons. But
the difference between collecting samples and Martian meteorites is that the Martian meteorite, we don't know actually where it's coming from.
Exactly,
so
exactly.
It's kind of like you would go out on the street here and you would, and you would pick a rock and you would say, what does this mean, this rock? It's kind of like you have to have the context. In geology, context is everything, basically.
Yeah. So no, it's absolutely right that we need to go and get samples from where we know where they are. But this idea that, is there possibility of lithopanspermia, it's called, right? This idea that life could have traveled between the planets. I've always liked the idea that, in fact, if we do find life on Mars and it turns out to use DNA, for example, the same as we have on Earth, that maybe actually we haven't learned anything at all. It's just that life has traveled between the planets and it's just the same. And in the weird way, because Mars has a lower surface gravity and it's easier to get stuff off Mars, that maybe statistically life started on Mars and actually came here through lithopanspermia. Or maybe we're all Martians. And of course, that raises the question in a sort of philosophical sense that finding life on Mars would be very exciting, very interesting. But if it turns out to be the same as ours, we haven't really answered the question of whether life can start twice. So that's why we need to look in the lakes of Titan or underneath the ice crusts of the moons of Jupiter and Saturn. Because, independent starting of life that's the philosophical question about, are we alone, right? I mean, there's a lot there, but...
Yeah, so I mean, if we did find, that would be the second question. If you would find extant life, say in the samples we bring back or on Mars, would be, is this a second genesis? Did it actually appear? I mean, I never particularly liked the idea of panspermia, that it came from Mars, because you kind of move the problem of how did actually life originate to another planet, which you know even less about. But I mean, I think it might be hard to know, even if we find that we're related. I don't know. Can we then answer that? I think it's going to be hard to answer which way it went.
Yeah, sure.
There's one important point that we haven't touched on yet, and that is the age of the landing sites. Sandra said that there were no plate tectonics on Mars, and therefore the rocks are more or less as they were deposited.
Well, except for the radiation and stuff like that.
Yeah, but and it's interesting to notice what is the relative age of the various landing sites. So Gale Crater, where Curiosity is now, is roughly 3.6 billion years, and that is already way into the period when Mars was getting dry. So the water they see in Gale Crater is probably the last gasps of in terms of water activity of the planet. Perseverance is going to a crater that is roughly 3.8 billion years in age, and that's at the border, 100 millions in more towards the drying phase. And the landing site of Rosalind Franklin is 4.1 billion years, which is smack on in the part where there was water all over the place still. So it will be interesting in the sense that by studying, admittedly it's different places, but by studying rocks of these three different ages, we may be able to tell a bit about what was the evolution in terms of interactions between waters and minerals on the surface, which is believed to have played a very important role for mediating we talk about the appearance of life, but really what we're talking is how do you go from a collection of molecular elements to a system that is able to work as a proto-life form, so to say. So there's big chances of learning a lot about not only if there was life on Mars or not, but also about what are the processes that are important that may have been active on Earth as well, but that we can no longer study here because of this cooking that Sandra was talking about. So I think these missions will provide a lot of information. Perhaps even we will be able to tell if the building blocks are different. We may find molecules that we think could have had the same function that they play on life on Earth, but that are different.
Excellent, good. Well, I think there's a lot to be learned. Obviously, that's where we keep going back to this crazy place. I mean, and on another occasion, we'll look at where humans need to go there and live. That's a whole nother question.
I just wanted to add, like I told in the beginning, that you don't learn about a planet by going to one place.
Yeah,
you go.
Absolutely.
If you want to learn about Mars, you have to go to several different places. So, and for example, covering, like Jorge mentioned, the different time periods. But even within the same time period, you could have different geology, because it's a planet.
Yeah. The one thing I always like about Mars, it's a smaller planet than Earth, considerably smaller, but actually there's just as much land on Mars as there is on Earth, because most of the Earth is ocean. So there's a lot of place to go and explore on Mars, and I'm sure we'll continue to do that for years to come.
But you touch an important point there, Mark. Because it was a smaller planet and it cooled down faster than Earth, the conditions for let's say, the window of opportunity for life to have appeared probably opened up on Mars before it did on Earth.
Another reason that we're Martians, right? And not the other way around.
and if I could extend it a little bit, but to kind of flip things on its head, if there's anything that we can learn from Mars, is perhaps just how precious our own Earth is, our own planet. And if things are potentially that rare, perhaps the implications are not just on what we can learn about Mars, but also how we see our own world as well. And so interesting and thought-provoking.
Can I comment on that? Because I tend to like, if people are saying, oh, if we don't find any signs of life, is that a failure, or, kind of. But it's not really, like you mentioned, is if you have all this water and you have all this chemistry and you still don't find any signs of, convincing, why is that? Maybe they're all gone, or is it because Mars was never, maybe there's something else that is needed for life to origin, to appear on our, we're learning on what is required for life to, origin on a planet, basically.
So. Like so much science, as an observer, it's not just about the answers, but also the questions that get thrown.
Yeah, I mean, also a negative answer, you kind of learn a lot about. Learn a lot from. So. Yeah.
Absolutely. Well, I have to say, on that note, I know where I'm going to be tomorrow evening as we kind of see these events unfolding. I suspect that you all might be near a screen as well, albeit for very different reasons. Sandra and Jorge, I say on behalf of everyone at Space Rocks, what an absolute pleasure to have you join. I imagine these are busy days for you in many ways, but thank you so much for sharing your thoughts and insight with us. It's been a real pleasure to meet you and to ask you some big questions.
Thank you, Alex and Mark.
Thank you for inviting us.
And before we go, we have a little tradition on Space Rocks, and it's goofy, but we've done it now for 38 episodes or something, so we continue. This is a test of our guests. What? You have to do it. So he's been watching. So we have a hand signal. So this is space. This is the Vulcan live long and prosper signal, and rocks. So everybody, if you can do it. Perfect, Sandra. Well done. You can. That's close enough. Close enough. You're a Martian. Look at it. That's only Martians can't separate their middle two fingers.
Is that the Martian?
No, this is the rocks. This is the space and rocks. Although it could be.
Could be. I'm thinking like Martian with the
little Martian antennae.
Very well done. Well, thank you so much once again, guys. An absolute pleasure. Thank you for your time, and hope to invite you back soon.
Yeah, and good luck for tomorrow evening, Sandra. I hope everything goes well, because you're one of our representatives on the Perseverance mission. And good luck to us in 2022 when we send the Rosalind Franklin rover. I mean, we've been waiting a long time. Let's get it done, right?
Yeah.
Well then, Mark, it's a big moment. It's what a stimulating conversation, and sometimes. I don't want to say proximity, breeds, any kind of complacency, but every now and then I do sit back from what's just about to happen and the kind of stuff that we get up to as a species. And it kind of does blow your mind what we're up to right now. I mean, it gets lost in the headlines sometimes, but geez, what a fascinating thing is about to transpire.
Yeah, and I think we had a discussion on with my good friend Jonathan Amos of the BBC on Twitter this morning about what are the takeaways from something like this, and I'm ribbing him because he's one of my best friends and he's a fantastic science journalist, but he kind of made the thing, it's just we're throwing a probe 470 million kilometers and landing it within 10 meters. It's like, yeah, forget the 470 million kilometers thing. It's that last bit and how you get down through the atmosphere, and then what you do when you get there. The fact that we can actually manufacture machines here on Earth and send them out into space to land on the surface of another planet, and then answer questions about where we may have come from or whether there's life elsewhere. It's kind of maybe it's a technological extension of philosophy, but it is utterly remarkable what we can achieve when we put our minds to it. So good luck to NASA tomorrow. It's a huge day for them, but good luck to everybody that's involved. UAE, China, Europe, all working together to understand, is there life on Mars?
Indeed, a fascinating question. I guess we'll get a little closer to an answer in the next 24 hours, fingers crossed. And, well, Mark, as ever, an absolute pleasure. Great to see you.
Yeah. See you later, everybody. Bye.